Welcome to Lab 3 on the black hole and orbits. This lab was split up into two parts. In the first part of the lab, we analyzed the motion of the unique trajectory of the star in order to determine the mass of the black hole that it was orbiting, using Newton's second law of motion. In part 2 of the lab, we determined the initial velocity required for our spaceship to take up a figure-8 orbit around the planet and a moon orbiting the planet. These are our results. The mass of the black hole was 1.13 times 10 to the 34th kg. Our initial velocity that we determined in order for the spaceship to take up a figure-8 orbit was 2.23 times 10 to the 4th in the x direction and 3.42 times 10 to the 4th in the y direction. First, we used the universal law of gravitation, which is shown below. We also used Newton's second law and the momentum principle. F net perp is the component of the net force that determines the direction of the trajectory. It points in the direction of the center of the osculating circle. This is equal to the centripetal acceleration, which is mv squared over r. F net parallel is the component that determines the motion of the object. Together, they make up F net. We also used the velocity update and position update formulas in order to move the star when determining the mass of the black hole. By rearranging the universal gravitation formula, we can solve for the mass of the black hole. Here's the computational model that we used in the first part of the lab. To the left is the calculation loop. Here we determine the initial and final momentums in order to calculate the rate of change in momentum. Next we set F net equal to the rate of change in momentum. Then we calculate F net parallel. Then we calculate the perpendicular component with the fact that dp dt perpendicular plus dp dt parallel is equal to dp dt. Finally, we rearrange the universal gravitation formula in order to calculate the mass of the black hole. To the right are the initial conditions including the mass of the star and the length of the time loop, which will be 700 hours. Here are the results from part 1 of the lab. This is a depiction of the star orbiting the black hole. Each value that is showing up below represents the mass calculated at the position. In the final step, we calculate the average mass of the black hole given the calculated mass at each position. The orange arrow represents the perpendicular component of the net force, while the blue arrow represents the parallel component. From this, we were able to calculate the average mass of the black hole being 1.13 times 10 to the 34th kilograms. Here's the computational model that we used for part 2 of the lab. In this part of the code, we found the r vector from the planet to the moon and the force of the planet on the moon. We also determined the force of the ship on the moon. Using this, we calculated the total force on the moon. Following the same steps, we also calculated the net force on the spaceship. Then we used Newton's second law so that we can move the bodies in our system. Then, through trial and error, we set the value of ship speed x and y necessary for the ship to take up a figure-8 orbit around the planet and the moon. Here are the results from part 2 of the computational model. This was the best we could get to a figure-8 orbit around the planet and the star. Through trial and error, we were not able to get a good representation of the figure-8 orbit. However, we could do more rigorous calculations that would take a lot more time in order to achieve this pattern in the future. We had two possible sources of error. The first one was that there will be a large margin of error because the figure-8 orbit was estimated through trial and error. This could definitely be more accurate using more involved calculations rather than just using brute force trial and error. We could have also decreased the intervals of delta t so that the average mass of the black hole is more accurate. What does it mean? The rate of change in momentum represents how momentum is changing over time. By Newton's second law, the rate of change in momentum is equal to the net force. The net force is equal to all the forces acting on the system at a given time. In this case, the universal gravitation force is the only force acting on the system. Thus, the rate of change in momentum and the net force both have the same magnitude. However, the rate of change in momentum describes an effect, while the net force describes the cause of the rate of change in momentum. What if? To model a new scenario where we'll include a planet, a star, a black hole, and a moon, we will need to include the forces due to gravitational interaction between the newly added celestial bodies. There will definitely be some interactions that are more dominant. This is because the black hole is significantly bigger compared to the other celestial bodies. the planet is mainly influenced by the star, the moon is mainly influenced by the mass of the planet since it orbits it so closely. Thus, there will be a lot of interactions that are more dominant. There are also weaker interactions, such as the interaction of the black hole and the planet and the moon. The moon also does not have much of a pull on the star because the moon is so influenced by the planet.